Hi folks, Mr. Long here. This is our first, second screencast overall in this part of the review. But this is the first one where we're going to do some real mathematics. So for this one here, there's some things that I want you to think of. So in this series of questions, we're going to define the function f of x as the integral, so the area under the curve from x equals 5 until x equals x. So it could be from 5 to 6, 5 to 7, 5 to 8. So in other words, if I want to find out f at 6, then that x needs to be 6 there. So it's the area from 5 to 6. Okay, so that's all it is. So that's the definition of that relationship. So what are some other things? So when I first get into a question like this, so it's first of all, when you read the description, it's probably going to say that f of x is twice differentiable, which makes sense, right? Because you want to be able to get the first derivative, the tangent slope, the second derivative, the concavity. It'll say it's continuous on a closed interval, right? So there's continuity all the way from there to there and includes those points, but it's only differentiable on what's called the open interval, right? So you can't differentiate right at the end point because you don't have a local linearity because it doesn't go beyond. So there's some other things that I would write automatically. So I see that f of x is the integral of g of t dt. Well, what's the relationship then for, and by the way, this graph is g of x. So if I differentiate both of those, I would get f prime equals g of x, right? F prime equals g. Because remember, when you differentiate an integral, they're inverses, so it gets rid of the integral. So f prime equals g, and then f double prime, the concavity of f, is the slope of g. This right here, you must do on these types of questions. If you do that right off the bat, it's probably helpful. Okay, so let's look at question A over here on the right side then. So it says determine the integral from 5 to 9 g of t dt. All right, well, that means the area under the curve from 5 to 9. And I'm just going to put g for short here because I don't have a lot of space. So that's going to be the area. So I start at x equals 5, so I'm right here at the x-intercept, right? So I'm right there at x equals 5, and then I have to move to the right all the way to 9. And I'm accumulating area as I go because that's what it means. Now this area right here, this area goes from this point here up to x equals 7. So from x equals 5 to x equals 7. It's shaded in yellow. Is that area below or above? Well, it's below. So it has the overall area of that is 5.5, but it as a signed area, is it positive or negative? Well, it's negative because it's below the x-axis. So then I would have negative, whoops, that would be negative 5.5. And this should be horizontal, but because again I'm running out of space, I'll do it vertically. This area here is negative 1.8. And by the way, you should be filling this in on your handouts. And then, now here's a tricky one. So look at this. So took an area here, right? So there's this area here above the curve is 1.5. Is that the area that you calculate, or is it the area between the curve and the x-axis? I know we say area under the curve, but what is really meant is what's the area between the function and the x-axis. So this is a little trick that sometimes people will put on an exam. So they look at that and they automatically go, oh yeah, the area under the curve is 1.5. Well, no, the area over the curve is 1.5. So what we have to do is count the squares. 1, 2, 3, 4, 5, and it's only 1 wide. So this whole rectangle here has an area of 5. Well, if the whole rectangle has an area of 5 and this is 1.5, 5 minus 1.5 is 3.5, and that's a positive area. So we would add 3.5. Okay. Now, if we add up all those areas, what do we get? Well, negative 5.5 minus 2 would be negative 7.5, so that's negative 7.3. Negative 7.3 plus 3.5, well, that's kind of like 7.3 minus 3.5. Which ends up equaling negative 3.8. Okay, negative 3.8. Now, that's the area under the curve. That's what this calculation is. Okay, that's what it's worth. Now the question is, what does it mean? Well, let's go to the definition of the original question. The definition of the question says that f at x equals the area from 5 to x. Well, we just did the area from 5 to 9. So what is that? That's f. Whoops, wrong thing. That's f at 9. Okay, that's what it means. Now, the other thing that we could do is we could think of it as that's how much the y value of the function changes by going from x equals 5 to x equals 9, which does make sense because there's more negative area than positive area. So the function, generally speaking, is decreasing, right, over this time. Okay, so let's take a look at some other questions. So in this one here, it's the same function, and the first thing we want to do is to determine f at 5, f at negative 1, and f at 7. So let's figure out what that is. So first thing, what is f at 5? And you know what? I'm just going to zoom. Oh, I can't zoom right now. Okay, that's fair enough. Okay, so what this says is f at 5 equals, it's going to be the integral from 5 to 5, because we know by definition, right? We know by definition that f of x just equals the integral from from 5 to x for g of t dt. Okay, so the first one is get the integral, get f at 5. Well, f at 5 is just the integral from 5 to 5. So how much area can you have if you go from 5 to 5? You've got 0. Okay, so the y value on f at x is 0. So that's actually how the function is set here. So this is set again from 5 to x. Sorry, that doesn't look very good. What they're doing when they do that is setting the x-intercept, basically. Is because from 5 to 5, the area is going to be 0. So your y value will be 0. Anytime these two numbers are the same, you can't have any area accumulate. So we're setting an x-intercept at x equals 5 by going from 5 to x. Unless there's like a plus 2 out here or something. Okay, so let's keep going. That's f at 5. Now we want to do f at minus 1. Well, what's f at minus 1 going to be? F at minus 1 is, now we have to work backwards, right? And I apologize, that's a very small writing. So we're going to go from, doesn't be writing. I'll try it up here. F at 5 is going to be the integral from, sorry folks, f at negative 1 from 5 to negative 1. Okay, integral from 5 to negative 1. Remember that when we write our integrals, we want to write them as, in this part we want to have the least, in this part we want the greatest number, so we're going to have to reverse this one and make it negative 1 to 5. As soon as we do that, we have to put a negative out front. So you can see here that that was done. Okay, so right there, we change the integral from, right there, from negative 1 to 5. And then what we do is we put a negative out front and we do our calculations. So what is the area going from negative 1 to 5? Well, this first area here, and again, it's one of those tricky ones. This big rectangle here is 7 by 1. That's an area of 7. The area above the curve here is 2. That's not your area that results in accumulation. Your area that results in accumulation is always between the x-axis and the curve. So if that's 2 and the whole thing is 7, that makes that area 5, and it's a positive value. So I've got 5 plus a positive area of 8, reading left to right, and then to get to 5, then I have to take away 4.8. That works out to be, oh, and then I get that answer and I have to multiply it by negative because I've reversed the direction. Okay, I've reversed the direction of the integral. So f at 1, negative 1 is negative 8.2. Then we have to do f prime at 6. And here's where we have to remember our relationships. Okay, this graph is g of x. What else is this graph? F prime, right? This is f prime. So you should always write on your graph something like f prime equals g. I would always write that on my graph. Okay, always, always, always. So when it's asking you for f prime, you know you just read the g of x value off the graph. So it says g at 6, so I go to x equals 6, which is out here. I go down and look at the y value and come across here, and it's 4, negative 4. Okay, so negative 4. So the y value on this curve, when x equals 6, is negative 4. What does that mean? That's the slope of f at x. Then we have to do f, this says f double prime. Okay, what is f double prime at 7? Well, f double prime at 7 is g prime at 7. So f, again, f double prime is g prime. What is g prime? The slope of g. So let's take a look at this. At x equals 7, which is right there on the graph, I go down, oh, and there's a tangent drawn for me. And that tangent has a slope of 2 over 1. Okay, so f double prime is g prime, right? Because I only have this graph to work with. So the way I get my answers, so you have to think about what are they asking me, and then what do I do with the graph or the table that I'm given. Okay, that's the big idea, right? So they're asking me for f double prime. The only graph I've got to work with is g. Well, what relationship is g to f double prime? G prime is the relationship. So I have to get the slope of this. So you can see where there's, this is tricky, right? Because you're naming graphs differently. Okay, and they almost always give you, in this type of question, they give you the rate graph, the first derivative graph, so that you can both integrate to go backwards to f, but then you can also differentiate to get the second derivative of whatever the given original function is. Okay, so that's 2. Now let's take a look at the next one. So does it say, so here it says, does the tangent drawn at x equals 3, so there's a tangent drawn here at x equals 3, right there, does it satisfy the mean value theorem in the interval from 0 to 4? So remember what the mean value theorem is. It just says secant slope over an interval is the same somewhere as the tangent slope. So is this tangent slope that specific one that we want that has the same slope as the average slope? Okay, tangent slope is instantaneous, secant slope is average. So let's get the secant slope. Oops, that's the secant slope. I'll grab that and move that out of there. So the secant slope. So let's take a look. So the secant slope from 0 to 4 is going to be, so f at 4, which is right there, that's negative 4, subtract f at 0, or sorry, g at 0, my apologies. So again, for this one here, does a tangent drawn at x equals 3 verify the mean value theorem for g of x? So in this case, we're just treating g of x as its own function. There's nothing about f. That's another thing that you want to think of. If the question doesn't have anything to do with f, you just treat g of x like it's its own function. Don't think of it as an original function. So sometimes you have to think of g of x as an original function. Sometimes you have to think of it as the derivative of f. Okay, so and each question is different. You have to read it and interpret. So for this one here, again, we do the secant slope, g at 4 minus g at 0. So it's going to be negative 4 subtract positive 4. That's negative 8, right? That's negative 8 there. And then the width is 4. 4 minus 0 is 4. That works out to negative 2. So the secant slope is negative 2. If the mean value theorem is verified by the tangent at 3, then we would definitely have a slope of negative 2. But if we look at this tangent that's drawn here, we can see that the rise is negative 8, the run is 1. So 1 over and 8 down. Well, so your tangent slope is negative 8. So no, the mean value theorem, MVT, is not verified at x equals 3. Okay, it's not. And so where would it be verified though, right? That's the question. So we'd need a slope of about -2. So maybe somewhere like that. That's pretty close to -2, right? So it looks like maybe at 1.5 or something, ballpark. Obviously, if you have algebra, it's much easier to do than just drawing a whole bunch of tangents and see which one has a slope of -2. Okay, last question here. Determine the equation of the tangent to h of x at x equals -3.7. Now on yours, it's got the actual ordered pair. So on the inverse, so you want an equation to a function h of x. As soon as you read these questions, you're going to be confused because there hasn't been anything yet that's been h of x. So that means as soon as you see something new, we're defining a new function. Okay, we're defining a new function. So h of x, and then you read on, and then eventually it says that h of x is the inverse of g. Okay, h of x is the inverse of g. And so let's start going down here. And it says that you want to find the tangent on the inverse, the tangent slope on the inverse at -3.7, 7. So if x equals -3.7, then that means on the inverse, that means y equals -3.7 on g. So what we know then is that the inverse function has -3.7, 7 as an ordered pair. Then what does the original function have? The original function has 7, -3.7, so we interchange that. Then what's the relationship for the derivative? Well, the relationship for the derivative is and sorry, you can't see that, can you? So if we want to get the tangent slope at -3.7 and h represents the inverse, then it's 1 divided by the derivative slope of the original function at 7. Remember, this is the x value on the inverse, this is the x value, the correlated x value on the original function. Okay, so we do that and we substitute in our values, and we can see, by the way, that the derivative slope of 7 on this graph is 2. Okay, the tangent is drawn there for us, so we know that it's 2 over 1. So I replace g prime at 7 with 2, and I've got my answer. Okay, so, and again, if you notice in that one, we're not dealing at all with f. So we're treating g of x as its own function in totally. Okay, last one in this set of videos, or in this video. So would a tangent to f at x drawn at x equals -0.5 be above or below? So there's some things that we remember, hopefully, about that. So first of all, would a tangent to f at x drawn at x equals -0.5 be above or below? Okay, they're asking about f at x. That's the first thing you have to know. I'm asking about f at x. Do you remember that property that shows whether tangent is above or below the curve? It has to do with concavity. When a curve is concave up like that, the tangent is always below. If a curve is concave down, the tangent is always above. Okay, so, and this here, f double prime is greater than 0. Here, f double prime is less than 0. Okay, so again, they're asking about f at x. So that means now I have to interpret that to g. So if I'm asking about f double prime, what is it about g that I'm measuring then? Well, that's f double prime is always going to be g prime. Okay, this is the part that's tricky. So here we go. Let's go through this. So I've put them together here, f double prime of x, which is the same thing as g prime of x. So if it's, here's our two scenarios. If it's less than 0, then it's above. If it's greater than 0, it's below. How do we figure it out? So I've got to go over here to the graph at x equals -0.5. That's -1, that's 0. -1 and 0. So what I need to do is, it's based on the slope of this curve. Now, do I need to actually be able to calculate the slope? No, because it just says negative or positive. So remember, the second derivative on f is the first derivative on g. It's the tangent slope of g. So if I go to negative 0.5 and I was to draw a tangent, it would look something like that. Is that tangent slope negative or positive? So we can see right here, here's our conclusion, right? Our conclusion's going to help us, or we're going to have our conclusion right here. Okay, it's less than 0. So that means, what does the curve look like? It looks like this, and the tangent will be above. Okay, folks, so that's our first video. We're going to have 3 of them on this problem type. But that's the first one. Please, again, rewind. Hopefully you're filling in your handouts and you're doing lots of thinking as you do this.